Anyhow, it occurs to me that before doing an update on PLFA, maybe I don't think, have I ever given a talk on PLFA to any of the people here? Would like to see my talk on PLFA? So you have. Right, so maybe before doing an update on PLFA, we should do explain what PLFA is. So this is based on a talk I gave in Paris. Xavier Leroy was giving a series of talks about things including proof assistance. So he asked me to come and talk about my work. And so I stole my title from Benjamin Pierce, where I stole lots of my good ideas from. So Benjamin, many years ago, gave a talk called Lambda, the Ultimate TA. Wow, 2009, okay. And his point was that if you're trying to teach programming language foundations, which is, of course, I was teaching, in fact, from his book, Types and Programming Languages, TAPL, that the students, as in any course, often get lost. But if you teach it with a proof assistant, when the students are confused about something, the proof assistant will straighten them out, right? It's very easy for a student to be confused about exactly how induction works. It's impossible for them to be confused about exactly how induction works if they're doing an inductive proof in ADNA or some other proof assistant. It's just not possible. It sorts them out. Now, there's a huge cost for this. The cost that Benjamin pointed to was that it's a huge amount more work for the instructor than paper and pencil. Now, he says it's between 1 and 2 orders of magnitude. I've done it now, right? That looks very scary. But I've done it. I don't think it's nearly that much. I'm not actually even sure that it's any amount more, because the ADNA does lots of formatting and so on for me and helps me make sure that I don't make errors. But what is absolutely true is it's way more work for the students. Probably not the order of magnitude, because that would be unreasonable to impose on them, but probably a binary order of magnitude, right? And what is that doubling about? It's just about dealing with stupid things like I forgot to declare that this operator is left infix or right infix, that sort of thing. I can attest that that's a huge problem for the students, because just the other day, I was working on some code that I was actually interested in, and I was delayed for a whole hour because I'd forgotten to make application right infix. I was complaining about this example I was doing. I couldn't figure out why. Everything had worked before. It was complaining because it was the first time that I was applying a function to 2 arguments. It was the first time I needed the fact that apply was right infix. It took me ages to think to go back to do that. So you will all know that if you're actually working with a computer system, there is just a huge amount of stupid things that go wrong. And just tracking those down takes a lot of time and is frustrating. So that's the cost. And then the benefit is that they're absolutely on rock solid ground when they do this stuff. So that's a huge help for them. So maybe I should go back and explain what I did. So what happened? So I bought that. So right, as a result of that, Benjamin wrote Software Foundations, which is a textbook based around Hawk. He's gotten many people to come join him, so it's grown into quite a large thing. Right. So there's Software Foundations, which came out of this. And it's got 5 or 6 volumes now, I think. But you can't cover that much, obviously, in a 1-semester course. In fact, I focus on exactly what's in volume 1 and 2. Logical foundations, which is just how do you use your proof assistant? What do logical proofs consist of? And then programming language foundations, which is, once we understand this, what are we going to do? And my original idea was, this is a great textbook, I'll just transliterate it into AGDA. And I started doing this, and I very quickly realized, well, it's not that great a textbook. In fact, I think in terms of the quality of the writing, TAPL is a wonderful textbook. It's really wonderfully written. This one, a bit less so, possibly because of that point that Benjamin made, that he was spending a lot of time getting the code right, and therefore perhaps had less time to get the English right. But there are just lots of small things in the treatment that I am less keen on. So I finally, I realized, well, I just want to write my own book. So that was what I did. And let's see. I happen to have just fallen in love. That is, by the way, this is something I greatly recommend for improving your productivity. Fall in love. So I was in Rio de Janeiro with Vonda, who wasn't yet my wife, but is now. And it turns out Rio de Janeiro is a perfect place for doing this sort of thing, right? Because the roads are paved with lambdas. They're everywhere. It's great. And so I just sat in the dining room. So that's me and my laptop. And that was my complete set of equipment. It was one laptop. And it turns out that was enough. You just sit down for a few hours every day. And after 6 months, you have a textbook. So, let's see. Show you the textbook.
How did the Rio summers treat you, Professor?
Sorry?
You look very red in that picture. How are the summers treating you?
How are the summers treating me?
Yeah, because it's very warm.
I grew up in California, so I'm okay. My kids grew up in the UK. They really hate it. And by the way, yeah, please do interrupt with questions if you have questions. They can be more technical next time. But so I wrote this textbook, Programming Language Foundations in AGDA. It actually has 3 authors. So I did all the writing, and then Wen, who's my PhD student, I was very, very fortunate to have Wen as a PhD student. She's marvelous to work with. But particularly, she just sat down and put together all the infrastructure for the book, and still maintains the infrastructure for the book. And on top of that, of course, I had her to teach me AGDA, which I didn't really know. I learned AGDA as I was writing the book. And then after the book was done, Jeremy Seek came along and wrote a 3rd part. So the book, right, exactly has 2 parts, right? Logical Foundations, which is just, here's how you use AGDA. And right, what we do is we start with, here's how you define natural numbers. So this is, right, just the piano definitions of plus and times, basically. And then induction, how do you prove things? Like that plus is associative, or that plus is commutative. And then relations, right? How do you define something like less than or equal on natural numbers and prove that it's transitive? And then finally, some technical backfilling. How does equality work? And I also define isomorphisms for them. Now, from the whole book, I made this one decision. And the one decision is, I will just stick to what is in the AGDA standard library. So there are all sorts of things there I don't like, but I thought just, I will stick to it. Because it's there, it's what the students will need to work with. It makes a lot of sense. And having, I mentioned falling in love is a wonderful improvement to productivity, but another improvement to productivity is constraints. Right? If you have certain decisions imposed upon you, then that makes it much easier. You don't worry about them anymore. So I just decided to wear this straitjacket of the AGDA standard library, and that worked fine. And there was only one place really where I deviated from it seriously, which is isomorphism. So you cannot understand the code for isomorphism in the AGDA standard library without understanding setoids. I decided that was too much for the students. So I just did my own definitions for isomorphism, but for everything else I stuck to it. One place where I differed is I put angle brackets around pairs when building a product type. And I've realized, no, the AGDA standard library is right, because if you want to build triples or quadruples or so on, it's much better not to have the brackets. types. It just works out much more easily. So I'm going to reverse that decision when I do a second edition of the book. Which, by the way, it's very easy because the whole book is online. Right? This is the book. I might try to talk to the publisher about publishing it at some point, but this is the right version. And of course, that's necessary because every chapter is written in literate AGDA, and so you want to be able to download it, play with it, and so on. In fact, the best thing would be if you could just look at it on the web and immediately alter the code on the web and have it check it for you. And there are some people that have worked with systems like this, but none of them work very smoothly yet. So I guess I'll have a wish list at the end of the talk, but if I had a wish list, I guess one thing I'd put in it is add it in JavaScript so that you could just do interactive textbooks. That would be really nice. But so the whole textbook just lives in a Git repository. And right, the amazing thing about writing in literate AGDA is it all gets checked in advance. And what that means is I'm absolutely certain that there are no errors in the formal language. I can't make this spelling error. The AGDA compiler would complain. So there's this whole huge swathe of stuff in the book that's absolutely correct, which is wonderful. But of course, all the English I write, that's not true. And I'm appalled to discover how many typos or misspellings or missing obvious sentences that ought to be there people discover. But the great thing is, since it's on GitHub, it used to be, right, if you wrote a paper, people would fix that by sending you an email, and then you would update the version of the paper, but that's hard because papers are supposed to be archival. Whereas now, people send me a pull request. I just click the button to accept the pull request. I write a short note, often saying just two very important words, thank you. When has already implemented software that means that when somebody does a pull request that we accept, they automatically get added to the acknowledgements of the book. Sorry, question?
Very good thing.
Yes, it's wonderful. Okay, so anyhow, and then you explain logical connectives and negation and how quantifiers work. They've already seen universals by now, but you need to explain existentials. And then how decidable works, which is very important in Blitz, right? Decidable is great because, right, around here, I explained to them that we don't have the law of the excluded middle. But, right, what is decidable about? It's not all the places where you do have law of the excluded middle. So law of the excluded middle, from being a triviality, turns into something incredibly useful. And then, tie it all together, I give them all the standard results about lists. So then, once they've got that under their belt, we can then learn about lambda calculus. So they just get how you define lambda calculus, how you prove progress and preservation. And this is what I would call an extrinsic formulation. So you have raw terms that are not necessarily typed, and then separate rules that assign them types. Yes?
I would address the first part is called logical foundation in solving propositions as types.
Oh, right. Where does propositions as types get covered? Is that what you're asking?
Yeah, or at least if you're using propositions as types before.
Propositions as types is covered here. Right? They just see it from the very beginning. It's part of the book. But that's a very good question. And that's one of the most important differences from Software Foundations. Software Foundations has one chapter on propositions as typed marked optional. So it's just hidden away. Whereas in Software Foundations, it's absolutely front and center. So this is the normal extrinsic formulation where you have variable names and you have raw terms and then you have separate typing rules and separate reduction rules. And then this is the intrinsic formalization based on, right, this old idea due to Torsten, Altenkirch, and Reyes. What's Reyes' first name?
Bernard.
Right. So this old idea that you can just have terms that have the typing rules built into them. So your rules for defining the terms just look like your type rules, and then you have separate reduction rules. And it turns out, I counted up the lines of code that I gave these. I threw out the examples and just looked at the lines of code. And doing it intrinsically is, well, it depends on which way you do the ratio. I did it one way with 0.6, of course the other way it's 1.6. And they differ from 1, which means it's the golden ratio. So using the intrinsic formulation. So there are two changes that happen there, right? One is terms are inherently typed, but the other is you stop using variable names and start using de Bruijn indices. Those two changes fit together very well, right? Normally, using de Bruijn indices is incredibly dangerous, right? You might forget to do an increment somewhere that you need to do. But if you can't write down something unless it's well typed, then all those mistakes are guaranteed to go away. Because if you do make a mistake and forget an increment, things end up ill-typed. And so I have complaints to you. So these two changes fit together very well. And this is just done for essentially PCF. This is also a difference from Benjamin's book. So Benjamin does the simplest lambda calculus he can with a base type. So his base type is Booleans. So he's just a bit short of full computational power. So I made a slightly different choice, and my base type is the naturals, and I also give them recursion fixed points over functions. So that's PCF, so they can do anything that's computable. And it's not really any more work, but then they get the full power of the lambda calculus. But that's all that they get. So the first thing they see just has functions, natural numbers, those are the only two types. And then here they learn about, okay, how would you do product types? How would you do sum types? How would you do the unit type? How do you do the list type? And so on. I do list type as an example of a recursive type, but I don't do recursive types in general for the same reason that I don't do system F, which is that then you need type variables. And it turns out that if you do, I mentioned that when you go from here to here, right, it gets smaller by the golden ratio. As soon as you try to do this at the type level as well, as soon as you go up to system F, it gets much harder. I'll say a little bit more about that later, but that's a real worry for me. I'd like to cover system F in the book, but it's difficult. And then I showed them a little bit about my simulations. I showed them bidirectional type inference, or simply type lambda calculus. That was yesterday's lesson, which was done in this room, by the way. And Monday, I will teach them the same idea about how to do untyped lambda calculus. And this is intrinsic untyped lambda calculus in that terms are inherently scoped. The other way to think of it is really typed lambda calculus where there's only one type. And Jeremy went and added these parts, and then he also added a whole thing on a very simple form of denotational semantics that he actually came up with, which I think has been underappreciated. So that's the textbook. What else did I want to say? So let me skip to something completely different for a moment. Right, there are the actual numbers if you want to know about extrinsic versus intrinsic. So 451 lines of code across 2 chapters, and then 275 to do the Bruijn intrinsic formulation. So when I did the book, let's get back for a moment. So at the time I did the book, one thing that bothered me is how am I going to animate what I'm doing, right? What you'd like to do is have this, right? They're doing it all on a computer. The obvious thing is you type in a lambda term, and tells them what the value is. Right? So the normal way I describe this is you want to be able to work out that 2 plus 2 is 4. And in Principia Mathematica, right, it's a very thick book, I think 800 pages or so, and somewhere around 400 pages he proves that they prove that 1 plus 1 is 2. And somebody, I expect it's Bertrand Russell, not Whitehead, puts in this snarky line about what it means if you have to get to page 400 before you're proving that 1 plus 1 is 2. I want to quote this line. I've never been able to find it again, so I always mention it. Does anybody know where that line is? It's around page 400 of Principia Mathematica.
I thought it was in the second volume, but maybe I misremembered.
I think it is in the second volume, yes.
Yeah. Okay, that's not narrated.
It's just a footnote that from these results now it follows that 1 plus 1 is 2.
There is that footnote as well, but there's somewhere a snarky comment about the fact that it takes so long to get there. That's, I think the thing, that footnote says we will see later that. It's when you see later that he makes the snarky comment. Anyhow, right, I want to be able to show my students, in fact, I don't do 1 plus 1 is 2, I do 2 plus 2 is 4. And I just want them to be able to evaluate the code. I thought, how am I going to do this, right? So there's things out there. There's the K system, which is specially designed for this sort of thing, but doesn't make proofs particularly easy. There's RedX, which is designed for scheme, which again is great for programming, but nothing about supporting proofs. So how was I going to get this animation, right? In Software Foundations, there's a special tactic in comp for doing this evaluation for you. But again, Agda doesn't have tactics, so what am I going to do? And it was about, I was well into the book, so something like 3 months of the 6 months, when I suddenly realized it's completely obvious, of course, that as soon as you've got progress and preservation proved, you get animation for free, right? Because, no. So this is the normalized tactic from Software Foundations. This is a paper on functional big step semantics, where they say, okay, if you do big step semantics, it's evaluating it for you. You could use a small step approach, and then what are the ones they cite? Exactly the K system and RedX. So they, like me, believe the only way to do this is with some system where it's built in. And the reason I'm touching on this on the talk is it took me a long time to see this. Of course, once you see it, it's completely obvious. Oh, right, further example is the Popplemark challenge. One part is prove preservation in progress, and a completely different part is animate. Do something that will actually compute a reduction step for terms, or even normalize a term. Well, of course, all that falls immediately once you've got preservation in progress, because what do? You just apply progress. It's either going to say it's a value, in which case you're done, or it's going to do a step, right? And this is in a constructive logic. So it says there exists an M, such that L steps to M, and it has to return to you the actual reduction rule and the actual term. Right? There exists an M, so it gives you the M, such that L steps to M, so it gives you the reduction rule. So now you've got the reduction rule, and then you can just recursively invoke eval again, and continue on your reduction. So you can actually build a nice reduction sequence, and if you run eval, it'll actually give you the reduction sequence in a more or less readable form. I had to change the formatting here, but this is actually exactly what comes out about 5 minutes. So you get all that for free, which is fantastic. So that's the background to the fact that so I consult for a cryptocurrency firm, IOG, that's a blockchain called Cardano. It's sort of one of the top 10. It was number 3 for a while. It's a very volatile market, so it went back down again. And we've got a team that works on smart contracts and so on. So the tool for executing your smart contract on the blockchain, right? Ethereum manages to regularly lose. Every 6 months, they'll lose another $10 million worth of Ether, either through a bug in a program or somebody exploiting something, a fault in Ethereum, to steal 10 million pounds. 10 million, by the way, is an underestimate. It's often 250 million pounds or what have you. So this is great for us, right? Because proving programs correct is really expensive. But it doesn't cost 10 million pounds. It doesn't cost 250 million pounds. So all of a sudden, there's a market for what we do. So IOG wanted to have a very simple programming language on the blockchain, one that you could prove properties of. And the one we settled on using was just System F. Right? And System F is a great thing to use because it was invented twice, right? Once by Jean Girard, once by John Reynolds, completely independently, on exactly the same system. So you can argue to people, right, this is not something arbitrary. So we actually use F omega, and we put in recursive types as a primitive, so that we can use the Scott encoding of natural numbers rather than the Church encoding, because the Scott encoding is much more efficient. But we actually use the Scott encoding. Well, there are built-ins as well, but we do use Scott encodings for data types. So we have no data types built in other than functions and for all and recursive types. And then you can write out the complete type system very compactly. And in fact, this is in this intrinsic form that I told you about. So,
could you make that full screen again, please?
Oh, sure.
Thanks.
Yes, it's very tiny there, but you want it slightly less tiny. So this is the actual address. So I sort of laid this out to begin with, and then I did one of the two important things that I ever did for IOG. So I've only done two important things for IOG. One is I told them to hire Manuel Chakravarti, and the other was I told them to hire James Chapman. They did. So I did this much, and then James did everything else. And it turns out that's really fortunate. So I've gone back to what James did. I thought, right, the intrinsic way is the right way to do things. Let me do an intrinsic formulation of System F, and right, James has already done it. So that'll be, so he did F omega, which is much harder, because you have to normalize the types. But just, even throwing away the F omega part, just having types already in normal form, I have found it impossibly difficult, even though James has already done it, even though my colleague Peter Tiemann went through and re-implemented all James' code, I've still found it impossibly difficult with two models to work from, which says something about the intrinsic formulations as soon as you go up to the level of having even minimal type dependency. So polymorphic types already is too hard. So I keep hoping, one reason intrinsic types is so easy is that Connor McBride and James McKenna came up with this wonderful way of writing substitution, where the trick is you have to do renaming first, and then you do substitution, which you might not think of, because renaming is just a special case of substitution. But once you have that trick under your belt, which is described in the textbook, it becomes very easy to do substitution. Before that, I think it was, again, impossibly difficult. So I'm waiting for somebody to find the trick that makes this easy. Now, Torsten Altenkirch, who unfortunately isn't here, did a paper on this back in 2016. I actually have a call with him later today to talk about this. So I'm hoping eventually we will understand how to do this really easily. But I wonder, I'm getting old. I'm thinking maybe instead of waiting for that, I should just redo the book to be extrinsic so I can tackle things like System F or like AGA and AGA. But anyhow, we have the proof. The proof is actually animated, and so it gives us a test version of Plutus Core, the thing that actually runs on the blockchain. And then the real implementation is in Haskell, and you run both against each other on arbitrary random programs as a way of testing. So we haven't proved that the implementation we use online is correct, but we do test the implementation that we use against the proof. Right, so I should round up, but I want to give you a quick wish list, since I'm talking to AIM. That seems like a good thing to do. Right, I just said doing all this stuff intrinsically is hard, but nonetheless it's really important, and you can just do it extrinsically, which I think is what Jesper's planning to do, right?
Yeah, intrinsically scoped, but not intrinsically typed.
Right, so we can use intrinsic. I suspect actually you might not even want intrinsically scoped, because I just mentioned how hard System F was to do. It's that intrinsic scoping, that use of deploying indices that makes it so hard.
Dependent types are easier than System F because you don't have the difference between types and terms. It's simpler.
Good, that would be great. That would be wonderful. Anyway, we need a way of doing this. I think this is the most important thing, to have better understanding. Right, years ago now, Behrendijk did pure type systems, which are a very tiny formulation, right? Less than half a page of formalization, and get you the essence of pretty much any dependent type system you could name. Well, no, there are interesting variations beyond that, but a lot of the important stuff goes just in pure type systems. It would be so nice if we had better understanding of how to formalize this and to get our students to do this. So I'm not at that point yet. I would like to be. This is a great room to talk to about that goal. If any of you are interested in that goal and want to talk to me about it, please do, because I think that's a very important thing to achieve. And in particular, right, we need AGA and AGA, right? COC is doing COC and COC now. So we need AGA and AGA. There are all sorts of huge benefits that will come from this. It's really an important project. Jesper, fortunately, actually has a grant to work on this, which is fantastic. But he's having trouble getting around to it. He's saying one reason he's having trouble getting around to it, he's worked on other things like AGA to HS, which Orestes has also been working on, and James. And people are really interested in that, so they bug him about it. So please, bug Jesper about AGA and AGA. I mentioned that the book has a lot of infrastructure. It does, Gwen set up the stuff that does continuous integration, right? I write things in .lambda and .md form, but right, there's also lots of support for .lambda and .type. There's pretty good support for all these things, right? This is amazing. It's fantastic that it's there, but some of it could be smoother. In particular, the CI stuff needs a bit of work. Andreas was talking about this before. So this would be something that would be lovely if people would look at. And then also, right, the NFC meta is such a wonderful tool for Haskell. Again, thanks to people in this room. And there is BNFC for AGA, but I think there could be better support for this. So this is something that'd be lovely if people would look at. And I expect I am past time, so I should round down that. Thanks very much.
Any questions?
So, about this problem of System F formalized. So the deeper reason is that you have now you have a quotient on the types, right? So types are, there's a non-trivial equality between types, like a decent system F omega, so you can beta reduce a type and then it's kind of still has the same semantics, but the syntax now needs to be quotiented, so to say, right? This seems to be the general problem making things hard.
It's not, so yeah, it's something like
this type conversion rule.
Quotient. So Torsten's system works in a type theory extended to support quotient types. So that's exactly how he addresses this issue. I guess I've got an example I can show you of a tricky piece of code that arises. Yeah, there. So this is just doing a map between an environment gamma and an environment delta, which is this is the trick to this nice substitution algorithm Connor and James had mentioned. But right, this is an environment for value variables. So it needs to be indexed by an environment for type variables. And then what we're saying is, well, there's a map from every value variable in gamma also appears in delta, but then we need to know every type variable in phi also appears in psi, which is what this map is. And then the types need to be adjusted by that map. And then you get, as you notice, the equations like, well, if we do the renaming this way and do the renaming this way, they're the same. You need to know that. And that's what makes it hard. So that every time that a type moves through a scope, you have work to do to prove some equivalences.
Right.
That's what makes it difficult. Yeah.
So you said, or you mentioned earlier that you have reduction, that you get preservation progress, and then you showed us this nice screen where it happened.
Yeah.
And you said that, well, here is 2 plus 2 is 4, but I didn't see the 4.
Oh, that wasn't 2 plus 2 is 4.
Oh, what was it?
It's, but you can do 2 plus 2 is 4. It's in the textbook. Let's see. There we go.
Okay, but then, I mean, do you have to write this by hand? I assume, right?
No,
This,
it's all
no,
by
no, no, that's the whole
unification.
point. This is generated by just saying eval gas 100.
Oh, I see. Ah, you
Generates
okay.
a trace.
So you copied this and then you prove it with that. Okay.
Well, you prove it with ruffle, and then you use the solver to fill in the things that are solved by unification. So you don't even need to copy paste it. You just
Maybe
kind of
just
tag that
solve it by
to
default, it will just write evolve
Yeah.
gas 100 again.
No, you can normalize the solutions that are in the solver by doing
Right, you
control
can
U,
do
control U.
control U.
Yeah.
So this whole talk should be in the form of a thank you to this community for providing this amazing tool. But one additional thank you I can layer on top of it is it turns out, let's see, I won't show you the code because we're past time, but you can use pattern declarations for your terms that you're evaluating. Right, so I do a pattern declaration for plus and a pattern declaration for 2. And then when I do so I didn't know that trick when I wrote the book. This has to be updated. But if you do it as a pattern declaration and then do the eval, it automatically looks for instances of the pattern. So you get something that's highly readable, because every time plus appears, instead of being expanded out to this huge lambda term, it just says plus, which is just amazingly readable. So who did that? They must be in this room. Who did the code that when you write a pattern declaration and it's printing it out, looks for instances and simplifies it back?
I think it would have been Andreas. No?
Oh, I think it was cool.
It's Ulf and he's not here. Somebody, please tell Ulf thank you for that. That was a brilliant
That's the display
summary.
forms, right? Let's do that.
Yeah.
It's, I mean, yeah. It's not the nicest part of the implementation.
Is anything the nicer part?
Something has to be. It's the gigabytes.
I've been learning lean. Lean doesn't have dependent pattern matching the way Agda does, and it doesn't have this great pattern trick. Those are the 2 things I've missed so far on learning lean.
Okay,
Okay, thanks.